well, Wednesday, the 10th of January, and we have been working with these tiny Atom M5 devices. So that's a LED matrix and a button as well. And it's got some other stuff in here that we'll have a look at today. So this stream was supposed to happen a couple of days ago and didn't, because I have had some dental work done and that was getting a bit painful. So I'll settle down a little bit now so we can get on with doing what I was hoping to do back then. But first off, I was going to introduce what we've been doing and sort of summarize that a little bit. So let's flop over here and share the desktop. So we've got a couple of these devices. And it turns out it's been handy that we've got two of them because I have been playing with MicroPython on them. And in the first stream, I found something with the MicroPython like helper class for these things that could be done a bit better. So because it is open source, we've gone and done it a bit better. And let me just see here. I can see that my microphone is not connected. I have pulled the wire out of the microphone. So I don't know if we are on the backup microphone. Let's just see. Ooh. Yeah, we are. So hopefully you can hear me. Okay, so I've got a useless Blue Yeti in front of me at the minute. Because when I moved it around on its arm, the plug came out of the bottom. I was like, why is that not lit up? Normally it's bright green. And there's nothing going on. That was just really confusing me. So hopefully you can hear me. If someone's out there in the chat, just let me know if you can hear me or not. But we'll carry on the assumption that you can, because I can see a sort of moving graph over in StreamYard for the microphone over there on the other screen. And I'm just going to double check that. And yep, test 1, 2. Seems like we're good. Okay, so we'll carry on. Fun with live streaming. Right, so yeah, we've had a couple of these Matrix ESP32 development kits. I wanted to do MicroPython with them as opposed to Arduino or something. So what I did was, in the previous streams, we went to micropython.org, and if you go to the download page and you do, oh no, not like that. Okay, you can basically find it. So here we go. Oh, it's M5Stack. So you can find this devices page on the MicroPython page. And down here, there's instructions for how to erase the previous, if any, runtime off of it and install your own. And you can download, there's like version 122, which is the very latest. I kind of need to look into that. I think the new stuff there is some SSL things. And what we did was we installed this and we played around with it and we wrote some code. So this is the device. This is the documentation site for the device. So it's got all of these different things on it. Let's see if we can oh yeah, make that nice and big. It's got a button inside the screen, so a clicky button. We played around with that. It's got 5x5 LED matrix. We messed around with that. You connect to it with USB-C. That was for powering it and also for putting data onto it. And this thing on the back here where it says HY24P, that's basically an Intel Grove connector. What I want to do in the next stream is look at using that for something so we can plug other things into it without desoldering. And what it's got in here that is not obvious what it does from this is this MPU 6886 thing. So what this is an accelerometer gyroscope. So we can tilt the thing around and we can determine what angles it's at and potentially how fast it's moving towards those angles. And what I wanted to do in this stream today was play around with that a little bit. So this is the device. I've got a couple of them. For scale, they are 24mm by 24mm. So as I say, here's one of them. It kind of is tiny and it's not very thick either. It's like 14mm thick or something like that. So pretty small. So when we went to MicroPython, what we could see here was there was a source on GitHub for this board. So if you click this, this will take you to the MicroPython project, and this board's an ESP32 base board. So in the ESP32 port folder, there's a board definition for this. And there's a MicroPython module in here that's like a helper class for this device. So it basically works with a couple of versions of this. There's this one we've got with the matrix, and there's one with a single LED on the front that we don't have. So it defines some pins for where everything is, and these are going to be handy. We're going to need those today for the accelerometer. The growth port we're going to use at some point in the next stream. And it defines a class with some useful stuff. So get the button status that we used before, or set the button callback if you want the event-driven version. And then we had set the pixel color. And this is where I started to think, oh, this is fine, but it doesn't work great with the matrix. So setting the pixel color takes a pixel number, and these things are 5 by 5. So if we set pixel like 0 to 4 is the first line, so if we set pixel 5, it'll be second one on the first one on the second line, and so on. And when we look at this thing like a matrix, that doesn't necessarily make sense, because we want it to present as something that has XY coordinates. So I was like, okay, I could write something and do a bit of a pull request that adds that, and maybe some other stuff like a equivalent get the pixel color at an X and Y. So in between streams, I went ahead and did that. And then there's two versions of this class. So this is like the generic Atom class that defines behavior that both the single button, single LED device and the matrix one has. And what I wanted to do only really applies to the matrix. So I thought, okay, let's put it in there. But let's just quickly have a look at what we had last time. So we've now got some code here. If you want to follow along at home, the code is in GitHub there. I'll leave that up there for a minute. And today's code will appear in there after the live stream, because I am going to do a little pull request that adds it. So that's where you find the code, down there. Where we got to last time was we basically did cheer lights. So we pulled in cheer lights information over an MQTT server. Cheer lights is a way of showing, showing LEDs in different colors and controlling them all throughout the world. So everyone that subscribes to cheer lights, if we set it to red through their Discord or other methods, then all the cheer lights in the world go red. So we implemented that. If you're interested in that, watch the last live stream. It'll be around on YouTube. And what I wanted to demonstrate really quickly was how we use this class here. So we can start up a REPL, and hopefully this is going to find it. Yeah, there we go. So we got the MicroPython there. This one doesn't have a build version, and you'll notice it was built on the 1st of January 2024. Because when I did my pull request to add this extra code to this class that we'll look at in a minute, I actually built MicroPython locally, and I thought this was going to be a monstrous pain to do. It was actually quite easy. The instructions are pretty good over there in the MicroPython repo. So MicroPython is a C project. It has Python scripts that help build it, so regular big Python ones. And between those things, you can tell it which board you're interested in building, so you don't have to build all of the ones that it's ported to. So I built an M5Stack Atom, and you get a firmware image that you drop on the device. And this one should have my new methods. So if we just do like import here, then what we can do is make this area bigger. So let's try and turn on some LEDs, and let's actually look at the device we're connected to on the second camera. So here, what we need to do is A equals new, is it new matrix, something like that. No, A equals matrix. I've had a couple of days off and I've gone completely. Oh, atom dot matrix. What am I? we imported Atom, right? So here's an Atom Matrix device. So now we should be able to call any of these. So we can do a.set pixels color, which will set all of them. And then we need an RG and a B. So let's go with a sort of light red. And you can see they all turned on red. And if we then do, let's try and control a pixel individually. So we want a.set pixel color, and then this needs a pixel number and then an RG and a B. So we'll try and set one to green. So if I pick 14 and then do 0, 16, 0, what you'll see here is one pixel's gone green, and it's the, let's see, 5, 10, 11, 12, 13, 14, 15th one across, because 15th one across if you start at the top and go across, down, across again, down. Imagine they're all in a long line. That's how the NeoPixel library treats them. So 15 there is that first one on that row, because we're counting from 0, so it's the 16th one on the screen, 15th one. Oh, sorry, no, it's 15th one. That's, yeah. You get what I mean. It's a 0-based counting thing, but this isn't that intuitive. I want to set, you know, X, Y. So what I did was, let's skip across to here. What I did was took this and did a pull request on it that added some other bits and bobs. So I added this set pixel color X, Y. So these are now X and Y coordinates. I'll make this bigger as well. And this is your color, RGB. And I put in, you know, a few examples of this. And I also wrote a get pixel color that takes an X, Y, does the opposite, returns whatever it's set to, and put a little blurry, unfortunately, picture in there. So this is my pull request. It's still open for now, but you can see how I changed the Atom class. So just down here in the Atom class, not the sorry, in the Matrix class, not the light class that affects the one with only one button, we have these extra values. So set pixel color XY, get pixel color XY. Now this device here, back to Thonny, is running my custom version of the code. So in week 1, before I'd rebuilt MicroPython and done this, I was using this utility function. That's now essentially being moved into atom.matrix. So instead of that, we should now be able to, so instead of a.set pixel color 14, 0, 16, 0, we should be able to do a.set pixel, what did I call it? Color XY. Okay, yeah, that makes sense. Color XY, and let's set, instead of 14, let's set 2, 4, and 0, 0, 16, set it to blue. And what you'll see there is that the third pixel in on the bottom row has gone blue, and that's because counting inwards we start with 0, so 0, 1, 2, and then counting down we start with 0, 0, 1, 2, 3, 4, so bottom and in a bit. And we can also basically say to it, well, hey, what's the pixel color at a given location? So let's say, what's the pixel color at 1, 1, and that should be red. Oops. So what did we? Oh yeah, you don't pass it a color. What's the pixel color at 1, 1, and we get the tuple, tuple 16, 0, 0 back. So it's red. It's R16 G 0 B 0. So that is what I've been up to improve things since the first stream. So you can't use this code yet in a production MicroPython build. We'll see if it gets merged. But it did, we have a look at this. Somebody added some labels to it. It failed a check commit message formatting rule, whatever that was, don't know. It passed everything else and nobody said, hey, fix your commit message. So we'll see what happens with that. But it's it's pending. So I did that, and as I said, this device has got the I think it's this one, the MPU6886, the accelerometer inside it. And what that is something that allows us to tilt the device and get information about that. And the obvious thing to want to do with that is build something that moves the LED, like moves an LED around the screen and bounces it off of the edges of the device or something. So you could build something that's just registering the tilt and maybe make a game out of it later or something. So I'm going to close a few of these. And what I've got in my own repo, so again, find that there, URL's down the bottom there. What I've got in my own repo right now is pull request, and I haven't merged that yet. It's still a draft pull request, but I went ahead and messed around and added some code that works with the gyroscope. So rather than live coding this, we'll just have a look at how that works, and that's kind of today's topic. And then in the next one, we'll look at this Grove connector, and I'll show you today some Grove sensors that I happen to have kicking around from a previous project. So I'm on this branch live stream 2 gyroscope. This will get merged into main shortly after this live stream. And I can close a few of these. Don't need that, don't need that, don't need that. So I started looking around to see what was out there that used the accelerometer, because if you look at, I'm jumping around a lot here, but if you look at this class here, this talks about neopixels, and it talks about defining pins for different things. So these are the I2C pins that we actually need for the accelerometer today. And this is the Grove port that we need for connecting with Grove sensors. And there's nothing in this class about the accelerometer. And should there be? I don't know really. I don't know what belongs in core MicroPython for a given device. But the accelerometer is a pretty standard part. So if you look up MPU6886 of MicroPython, there's some resources out there. And one of the ones that I found was this, which I'll make a bit bigger. It was on this site, hackster.io. I'd not really come across this before, but simple MicroPython code for the 5x5 LED atom matrix. That's what we've got. And it's built-in accelerometer. That's what we've got. So it works with some other devices. We don't have those. And this roughly does what I wanted to do. It just bounces around. So I sort of took this code, borrowed from it, refactored it a bit to use the MicroPython helper class, and we'll take a look at that. But basically, they've got, if you have a look here, it's quite a nice little write-up. Here's the hardware. We've got that. We don't have the M5Stack with the flash hat, but I guess that's another M5Stack device that you could use. We covered off installing MicroPython. I'm going to stick to regular production MicroPython, so not the one with my extra methods in it. So I'm actually going to quickly swap devices here, because that one's got the custom build on it, and it's now got a nice mess of blue tack on the back of it because I stuck it down to the board. Right, this one here does not have the custom build on it. It just has the regular one, so we can't use my extra pull request code, but that's okay. Obviously, this would work on my extra pull request version of MicroPython 2 because it just adds things. It doesn't take anything away. But I wanted to do it with the version that you could get hold of right now and do it on your own device. So we installed MicroPython before. That's out of the way. That was stream 1. Go watch that on YouTube. And let's see, we burned MicroPython. We know a bit about working with MicroPython. We've got Phony. And here's a nice diagram with an aircraft of basically the sort of movement that this sensor can detect. So we want to really look at two things because we're working in two planes here. We're going to show the output of the sensor on a screen that is flat and 2D. So really, we want pitch and roll. So we're going to use that as if there's a marble on the sensor and move it around the LED screen. Yours not that particularly relevant to what we're doing here. So they've also got some code. They've provided a library for the MPU6886. It's an I2C device, which is the protocol it uses to talk to the M5Stack and how we access it through MicroPython. And it's got all the code we need and a nice class. And basically, we just get to turn this thing on, set some sensitivity defaults, and then basically ask it for acceleration information. And we get AX, which is the sort of vector of movement. Vector of movement? I don't know. Is that the right thing to say? But we get AX, AY, and AZ, or AZ if you're American, which are the sort of three ways it's moving. So they can be translated to pitch, roll, yaw. And we need some helper code to translate them to actual angles. Then the idea of the code that they've got here in the main.py is to, when the thing goes over a certain movement threshold, sort of angle, tip angle in either direction, to start moving the dot on the screen, and when it's back under that, to stop it. And obviously the angle can be positive or negative, and then we're going to go one way across the screen or the other way across the screen, depending on which one that is. And they've got, basically, I kind of didn't borrow much of this code. So this MPU 6886 driver class, I pretty much took that verbatim. I don't think there's any changes in there. This one, I did change quite a bit. So what I did borrow was they have a compute angles bit of code here that takes those AX, AY, AZ values and calculates pitch, roll, and yaw as angles, doing some maths. I am not the best mathematician, but luckily they also provide a nice blog post entry with, again, the same sort of plane metaphor and some explanation about how the maths works for how you get an angle out of that. I'm not going to worry about that. We're just going to basically trust in the it's standing on the shoulders of others who've done the maths. So I kind of used this, and then I didn't use the rest of this because their code here is using the raw NeoPixel library, and they've got some ping constants here, and all of these things are defined in the Atom Matrix helper class in MicroPython that maybe didn't exist when they wrote this. I don't know. So I went with that, and the takeaway here is there's some maths in here, and we're going to use that to do something. So what we need to do is go back to Sony, and let's close up all of this code, and let's move this around. I wish this would have a wider point where you can grab this shell and move it up and down. It seems to be really picky about where it wants to do that, but there we go. Right, so there's a folder after this pull request has been merged. It'll be on main. At the minute it's in a branch called second live stream. It's got 2 files in it. MPU 6886 is their library for the accelerometer, so that's just a straight copy of that. We haven't changed anything. And then main.py is my version of their example code. So this has been changed quite a bit. And what we are going to do here is just have a quick look at how this works. So first off, I'll just connect to the device. I think we've got, I need to plug it in. That would be helpful. So this might wander around because I can't blue tack this to the map because we're going to pick it up and move it. So let's see what we've got here. So, all right, we've got a MicroPython. See, we're back to 121 that was built on 2023, October the 6th. So not my custom version. This is one you can get at home. And there's one file on the device at the minute, which is just a copy of that MPU driver. So when I run this main file here, what you'll see happens is we start to get a lot of output. And as I move the device around, you will see that oops, try and keep it in the center. You will see that the pixel here moves around the screen, and we're getting a lot of output from the accelerometer. So oops, let's try and leave it. With this zoomed in so much, any little movement on the desk, let's just pin it with the blue tack for now. There you go. Any little movement on the desk translates to a big movement in the camera area. So you can see here that it's at rest now, the dot's where it was. If we move it, it moves around and we could eventually get it to land in the center. But the dot moved again. The dot is moving based on the orientation of the device, and we're getting lots and lots and lots of pitch and roll information out of here. We're not using the yaw information at all. I can't represent that on the 2D screen, so I just removed it from the code. It's kind of calculations that the device doesn't need to be doing and output that we don't need to be dealing with. So I'm going to stop this so that we don't get all of this distracting input, output. And let's take a look at what we've got. So some stuff that's common from before, we're importing the atom class from MicroPython, that's fine. We are importing time because we're going to want to do some sleeps. I've imported the whole math library because their bit of math here is doing stuff with trigonometry, so we need functions for that. And also some constants, so pi. So that's that angle calculation code that got straight lifted from the example code that I found, and that's where the explanation for that is. But basically, you feed it in an AX, AY, and AZ that come back from the accelerometer, and you get back angles. And there was a third line in here to calculate yaw, which I don't need, so I just removed it, and then it returns a pair of pitch and roll values in angles, which we can then use to say, oh, okay, is this above our threshold angle? And we've set our threshold angle to be 5 degrees. So at plus or minus 5 degrees of movement, the dot is going to start moving if it can. It can't when it's already hit the edge of the screen like it has there. So, oh yeah, I'm not running, so it's not going to move. Let's just move that. So when I do this, you'll see it goes across, 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 and up and down. But when it gets to the edge, it stops. And their code that I found on the net also changed the color of the dot when it bounced off the edge, but I left it as is, so it always stays red. Kind of just simplifies the example a little bit. So we've got, let's see what else we've got in here. We've got this utility function that is my one from the previous stream. So it sets a X, Y position, which is handy in this case because we're only moving one dot around the matrix and we want to know when it's hit the edges. So that sets the XY position to a given color. And the way it does that is it works out how far down the chain of pixels that XY position really is. If you assume 0, 0 is top left, 1, 0 is the second row on the left, and so on, and all the way down to the bottom. So that does that. Compute angles is essentially library code. It came from the internet. And then we've got a calculate new position function. And what we've done here is basically this calculates both the X and the Y position. You call it twice, once for X and once for Y. Because our matrix is a square, it's the same number of pixels across as it is high. We don't need code to deal with whether we're talking about X or Y here. So we just pass in a position. So what number the dot is currently at, the angle that comes back from the sensor, comes back from feeding the raw sensor data into compute angles here. And yeah, interestingly, I've got size there. I don't think I need that. That is probably something that I was thinking about making this more generic, and then I realized these devices always have 5 by 5, so what's the point? So let's remove that because we don't need it. Right. So save that as well. Have to remember to commit that later. So basically what we're then saying is, if the angle is greater than the movement threshold, so the movement threshold is 5, if it's greater than 5 degrees, and the position of the device in whichever plane we're looking at the minute, the X or the Y, is less than 4, because we have 0, 1, 2, 3, 4 of the 5 pixel positions, then we're going to move it across 1. And if the angle is less than negative the movement threshold, so -5, and we are greater than 0, so if we haven't hit the other side of the device, or the top, so the left or the top, depending on which orientation we are asking it about, then we're going to take 1 off the position, and then we'll return the position. And then basically we need some code that sits in the loop, reads the accelerometer, gets the values back, calculates the angles for them, and then runs this calculate new position a couple of times to get a new X and a Y and move the dot there. So we'll see how that works. In order to do that, we have some setup. So we've got to set up an I2C connection, and that needs a couple of pins. It's what's called an SCL pin and an SDA pin. And again, I hard-coded these. And where did I find that information? Well, I found it from looking at the, I think it was the documentation down here somewhere. Somewhere down here, there's a diagram. Here we go. So there's this diagram here. And it tells us what is going on. So how this device is wired up. So we wanted SDA and SCL going to the MPU 6886. So if we trace these wires back, SDA goes to GPIO 25, SCL to 21. So I got 25 and 21. However, I then realized this morning that if we look at the MicroPython class for this device, I think they've defined them as constants already, because I talked about it earlier in the stream. So we could just use the constants that are in the class. So let's do that, and then we don't have to have hard-coded values. Not that these things are ever really going to change, but so it's these two things. So we could just use those instead of my hard-coded numbers. So let's just paste that in here a minute. And I probably need to call those atom dot. Try that out. So that's the SDA one. So SDA equals pin, and then that, and so on. This is not really that important, but you know, they've provided constants, so we should probably use them. So atom.scl pin. So let's have a look and see if that actually works, and also just quickly look at where I'm calling calculate new position, see if I was ever passing that third argument in. Yeah, I was passing in 5, but that was totally redundant, so don't think we need that. We'll come to that in a minute. Okay, so watch this either work or blow up. So it's working. Does it work in the other orientation? Yes, it does. Okay. So our constants work, and our tidy up of this calculate new position function works. So I'm just going to quickly bank that in GitHub. Do that. Second stream main.py. Might as well push it. Right. Okay, so that's there, and it'll appear in main when we merge this after the stream. So where was I? Yeah. So we have to set up an I2C or I2C connection. That involves a couple of pins. Those pins now have constants, so we don't really need to know how it's wired up. And then we have to create an instance of the driver for this accelerometer, and that takes that I2C information, so how to connect to the accelerometer, where to find it. And this is a constant from this module that tells us basically how accurate, how often we want the thing to check in the background. So we have set AFS 4G. Let's go and have a quick look at what that might mean. So resolution and scale, 4G. It could be potentially more accurate than that. I've found that's a reasonable approximation for the sort of speed of movement and detection that I wanted. So you can play around with this. There's also gyro config in here if you wanted to use the gyroscope. We're just using the accelerometer for this. So let's put that away. So we've then basically got this MPU 6886 that we can call functions on. I've created, like in the previous code, an instance of Atom Matrix. That's going to deal with everything to do with the LEDs. And we started by setting all of the pixels to color off. Color off is a tuple of 0, 0, 0, so black basically. And because this expects separate RG and B parameters, we just use the asterisk there to unpack that into those three things. Then we have a start position. So our start position is dead center. So 0, 1, 2, 0, 1, 2, essentially 3 across, 3 down. And then all this code does is it just runs in a while true loop. So run forever, because again, MicroPython, there's no operating system. We have to be like doing something or waiting for some event or something. So we are running all the time, and we are calling the get accelerometer data function here in the MPU 6886 that we've established. So that goes and queries the sensor and says, hey, give me your data. And those values that come back are not angles. They are raw values that look like this, for example. So you get these values back, and then you have to do a bit of math to calculate the angles that we want to then check against our threshold. So I'm just dumping those values out, and then we're passing them into the compute angles function. Again, it takes AX, AY, and AZ. I removed the yaw calculation from this, so there isn't any, like, the original code had something like that, and we don't need that information because we're not using it. So it then tells us what the pitch and the roll are. And then what we do is turn off the pixel, so that wherever we're currently located, we'll turn that off. If nothing's happened, we're going to turn it on again in the same location, but we always turn it off using my utility function. So again, when my pull request, assuming it gets thrown into a release, you just do atom.setPixelColor x, y, and you wouldn't need to define that function. So yeah, this turns that current pixel off. Then we calculate the new positions based on the pitch angle and the roll angle. So the pitch angle is the x-axis for us, and the roll angle is the y-axis. And either the thing will have changed position or it won't, depending on what the accelerometer tells us. If it's above 5 or below -5 degrees, it will change one direction or the other. And then we basically turn on the new pixel position to be red and go to sleep for a tiny amount of time, so that we're not just constantly burning up the sensor. And also so that when you don't touch it, you know, the whole thing just doesn't go shooting across the screen. So when we run this, you'll see left, right, up and down, and so on. And it's very hard to get it to sit absolutely straight because there's a big lump of blue tack under here that's stopping it. Hey, there we go. That is stopping it from rolling around on the mat or the USB cable from twisting and pulling it. So you can see that in this sort of steady state, it's got a very, very, very slight angle on, but nothing big enough to concern it. It's actually pitching quite a bit, so it is not exactly level on there. But if I remove the blue tack and we try and put it flat on the desk, you'll see it pulls all over. If I put the blue tack on the side, maybe that will help it a bit. Yeah, we've got much lower pitch and roll now. We're like at 0.0 something or other. So yeah, that's the accelerometer. So again, this thing costs like, what was it? This thing costs like $15.50, or probably about the same in pounds if you go to one of the UK suppliers like Pomeroni. It's got a lot of stuff. So we've got these 25 LEDs that can be all different colors. We've got this is a button, remember from the first stream. We've got this accelerometer that we can use to move things around and react to that. And then it's got, I'll pick the other one up. It's got this other connector on the bottom. So that sort of black one at the top is a USB-C. The white one at the bottom that's actually a little bit bigger, that's a Grove connector, which is a standard for connecting different sensors. And you'll see in the code here, I mentioned it earlier, there's some stuff about the Grove port. So what I want to do in a third and final live stream about these devices is use this Grove port to do something. But for that, we need some Grove compatible sensors. So let's just switch around to looking at this. So if you go on my website and you have a browse around, you will find, well, you want to know where my website is. So if you go here to the URL at the bottom, simonprickett.dev, and have a look around, you will find that I did a series of live streams, and there's an article on the website and a little code base building things with this, which is the Seed Studio Grove kit for the Raspberry Pi Pico. So a different microprocessor, a different company providing this. But the cool thing with Grove is it's standard. So all of the sensors that I have from this kit, and there's quite a few of them. So you can see here, it's got, let's see if we can enlarge that a bit. It's got, what do we got? 5 sensors, 5 actuators, 2 LEDs, an LCD display, and a Grove shield, which we don't need. That's the thing that you plug the Pico into. We've got a Grove connector here on the base. So I've already got a few of these sensors. We can actually have a quick look at a couple of them. So there's the connector here. Let's make this a lot bigger. There we go. So there's the connector here. Let's get rid of that banner that's kind of in the way. Let's get rid of the banner that's in the way. There we go. There's the connector. And then I've got this is a temperature humidity sensor. So for scale, it's kind of about as big as the device itself. Then we've got this one's the light sensor. And you see they all have these standard plugs on. And this, what else have I got out? This one is a mini PIR motion sensor. Again, standard Grove plug. So we have got some toys that we can play around with this. And we've also got a whole load of these. Let's get both ends. This magnification is really messy to deal with. We've got a whole load of these Grove cables that we can just plug into the bottom of the device, and then let us make me a bit bigger. If you go sort of here, we've got there's only one way of plugging them in, and I'm sure I can manage to still get it wrong. There we go. So we've got a cable that plugs into the back of this device, and then we've got something that plugs into the other end, and we can pick up any one of these sensors off of the desk, and we should be able to just connect it. So now I've got my M5 device, and I've got my, which one did I go for? The PIR sensor. And what we should be able to do is use the MicroPython code that Seed provided for the sensor, and we should be able to, let's swap back to swap back to, where's my desktop gone? Nope. That's better, isn't it? Right, so we should be able to use the demo code that Seed provided for all of their sensors. And I think this is the Pico with all of the sensors attached to it, like a great big spider. So you actually get lots of cables in this kit. It's not cheap, it's $40, but it's pretty good. And I always try and be very transparent. I didn't pay for mine. Seed actually sent it to me to play around with, but is it value for money? Yeah, absolutely is. You get all of this stuff. And here we go. Learn and documents. They have got lots and lots of documentation for how it all works. So if you, for example, wanted to do temperature and humidity, they've got code, it tells you very explicitly where to plug everything into their Grove shield because it has multiple Grove connectors. We've only got one Grove connector on our little, let's get rid of these, our little M5Stack here. Oh, it's going to sit on its edge now. I've plugged something into it. This is where you stick them down to the desk. So we've got one Grove connector, keeps falling over, one Grove connector there. So we don't have that complexity. But as you can see, they've provided us with MicroPython code that, oh, this one does buzzing, sorry, temperature and humidity, here we go. So their project uses an output, so it uses the Grove screen it comes with. We've got the LEDs. We can only plug one of these things in at once to the M5Stack, so we've only got one connector. But yeah, so we can use the temperature and humidity sensor. It looks like we can just read that. It looks like there are library modules for some of the sensors. So for example, here, and then they've got links here for those. So DHT11, I know is the one for the temperature and humidity sensor. And when we click that, you'll see it goes to Seed's GitLab, and we can just copy this into our project. So what I want to do on the next stream is mess around with this sort of thing and the Grove sensors and sort of demonstrate the one missing feature of this device that we haven't looked at, which is adding other things into it that obviously cost more than the original $15, £15, whatever you paid for the device that you've got. So yeah, I haven't done this yet. I will go away and mess around with maybe a couple of these sensors so we can unplug them and plug another one in. But I'll definitely try the temperature one because that's an easy one to relate to. And I'll have a think about what we can show on the screen. So maybe when we do some movement, have something show on the LEDs and have it settle down when there isn't any movement, for example. Or with temperature, I suppose the obvious thing would be a threshold, and I'd put my hand over it and heat it up, send it above the threshold and have the screen react. Similarly with light, I could always cover it or flood the light with the torch from my phone. You'll see me do that on the recent live streams I did with the Pi Hut Advent calendar. So yeah, that's it for today. I need to replug my microphone in because there's this big microphone in front of me that, as I said at the start of the screen, was slightly confusing me because I'm used to seeing a green ring around its volume button and there was absolutely nothing. And it turns out I'd unplugged the USB connector whilst moving the boom arm for it. So there's yet another thing that needs to go onto the live stream checklist. So this stream was brought to you by the iMac's inbuilt microphone. Hopefully that's been okay, and I'll find out afterwards when I play it back. But yeah, so if you want to keep an eye on when I'm doing this next, go follow me on, we're still calling it Twitter on this channel, and that is going to stick. So follow me on there. And I generally announce these things a couple of days before I do them. And as long as I'm well and I'm off to the dentist again next week, so I'll try and get it in before then. Maybe Friday this week, can't promise. I try not to do weekend ones, try to do other things on weekends. So we'll see. But yeah, that's that. The URL for the code for this is in the video description if you're on YouTube. It'll be there on Twitch shortly afterwards, and I don't think the other two platforms, LinkedIn maybe, probably not on Twitter, but anyway, you can find it there, and I will merge the pull request that I was working on to add today's stream code and the extra changes that we made during the stream today, so you'd be up to date. But yeah, if you want to ask me a question about any of this stuff, again, the best place to do it is Twitter, or if you don't want to do that in public, go on my website. There's a contact page, there's an email address. You can always send me an email. I do try and get to them, but I can't promise any sort of turnaround time. Okay, so I will leave you to the rest of your Wednesday. Far enough into the year now that I remember what year it is, and I'm getting okay with what day of the week it is as well now. But yeah, I'll leave you to your Wednesday. Mine is going to involve playing around with growth sensors a little bit and figuring out what we can do in the next and final stream for this particular project. Then we'll have to think of something else to do on these streams, because I do want to keep doing them. Probably not daily like when we did the advent calendar, but maybe like once, twice a week. So see what we can think of. I've got a big project backlog in the IKEA drawers behind me of stuff that I wanted to play with. So pick something out of that and do it. But if you want to suggest something as well, or if you just want to send us something to play with, I'm always happy to do that. All right, take care. See you next time. Bye.